I I couldn't resist the Nichols theme on Jupiter because it sort of reminds me of Jupiter anyway. Well, isn't that beautiful? That is amazing. That is just amazing. I think that's from Juno. It's one of the recent ones because you can tell the resolution. The cameras are brilliant. You know, they're just phenomenal. Um, right. So I was going to concentrate tonight mainly on the inner moons and particularly on the Galilean moons. But before I begin, we'll just sort of show you a bit about the Jovian system, which is rather interesting. 95 moons, which means that Saturn has thrashed Jupiter in the stakes for moons because Saturn's got 146 and Jupiter's got 95. So Jupiter is no longer the king as far as the number of moons goes, although there are a lot of moons they haven't named, as you'll see, and lots that they keep discovering. They reckon there could be about 100 retrograde moons that they still haven't named or anything. So anyway, it's still not going to match Saturn. So the most massive, those four, Io, Europa, Ganymede, and Callisto. Now, I will tell you there's an interesting stuff about this because they were simultaneously discovered by Galileo and this guy, Simon Marius. His real name was Simon Mayer, a German astronomer. And they had an almighty fight over who discovered what first. And then they had a massive fight over the names, as you'll see. And I've got a little bit about that later on. But coming down to that, so lots of moons have been discovered from 1892 onwards, but the Galilean moons are by far the most massive, and in fact, they are bigger than any of the dwarf planets. So even Pluto. So that's quite amazing when you think about it. And in their own right, if they weren't going around Jupiter, they would deserve the title of have it be a planet. It's just that they're satellites of Jupiter, but because they've got sufficient mass and gravitational pull to be qualified as planets in their own right. So there are 91 moons. So Galilean moons are the most massive. The remaining 91 account for only 0.003% of the mass of the satellites going around Jupiter. So that means that those four moons are 99.997% of all the mass of the moons going. They are truly big, and in fact, Ganymede, as you'll see, is bigger than Titan. Ganymede rules the roost. The remainder of the moons, the others, apart from the four Galilean moons and four others I'll talk about called the inner moons, which are the closest, and in fact around the ring system, located around the ring system of Jupiter. All the others are irregular and mostly retrograde. So they've been captured and they're spinning in the opposite direction to the planet. So the inner moons are prograde, but the outer moons, most of the outer satellites, not all of them, are retrograde in their orbits. I will try to whiz through these. A lot of notes, but don't worry, I'm not going to read all the notes. It's just for me. So I can look back and remember things. So Jupiter's expected to have about 100 irregular moons. Now, this is a diagram of their paths. Now, there's a little video, a great little video of this, and it's mesmerising to watch because they show the ones that are named in the red paths, red orbits, and as well as all the others, and it's just incredible to watch. So 100 irregular moons larger than a kilometre, plus around 500 that are smaller retrograde moons down to 800 metres. So that's pretty small. They're just bits of rock, really. Mostly captured asteroids and other things. Probably bits of stuff left over from the formation of the solar system, and it's just accumulated around the planet. Of the 87 known irregular moons of Jupiter, 38 haven't even been named. So anyway, there's the orbits. The purple denotes the Galilean moons, the ones closest to Jupiter. Yellow for Themisto, which is a really an oddball one, going, as you'll see, its orbit's strange. Blue for the Himalaya group, cyan and green for Carpo, and Valetudo, another interesting moon, but very small, respectively, and red for the far-out retrograde moons. Now, when you see this in motion, it's great. They're the ones that are named anyway, as of January. Prograde in blue, meaning going west to east, as Jupiter does, spinning in the same direction, and the others are going in the opposite direction. And the general thing is in science that things that are retrograde have been captured and things that are prograde have been there from the formation. And in fact, the Galilean satellites were there from the protoplanetary cloud around Jupiter, I suppose you could call it, from the beginning, as far as we know. Yeah, that's interesting. I don't know the physics, but I suspect from collisions like where we are, what's the next thing? The Kuiper Belt, where things get dislocated from collisions. And there's going to be some, by the way, there'll be some collisions happening. One of these moons is going to collide with the others. I'll tell you about that shortly. So I think, Stefan, you might enlighten us on the physics, but I guess a lot of these things are, they might have come from a different direction. Don't know. Would that be the case, Stefan? With the retrograde orbits? Yeah. Huh. Yeah. Anyway, so yeah. So research. I mean, I just can't delve into all that stuff because I don't have a background in anyway. So, but I love this because this is the whole system in three different levels of magnification. So at the top, you can see the innermost moons, Adrastea, Metis, Amalthea, and Thebe. I'll talk a bit about those shortly. And then just the closest to the Galilean satellites, Io. When you pull out, you've got the Galilean satellites in the middle panel. So the ones we just saw are inside Jupiter's ring. You can just make out a slight ring there. They're inside, that's where they are. And then, and it says here, can you see that? That's very faint, I'm sorry about that. That says main ring, Amalthea ring, and a halo ring, which is the innermost thing. And all that is just very fine, particulate asteroidal matter, I suppose. Rock, ice. Sorry? From Io. Oh, yes. Now, coming to that. That's next. Oh, and the bottom one, it just explains, that's further out as we move right out. You can see millions of kilometres here, and they've grouped the asteroids, the retrograde ones, into groups for the sake of naming them. So Himalaya group, Valetudo is the one that's on its own. And where is our friend? Oh yeah, Themisto, which is the nearest of the inside the outermost moons. So anyway, that's the entire system. Millions of kilometres. There's some of the outer ones have got a hugely great orbit, massive orbit, quite a way away from. If you imagine that in terms of Earth and Moon, that's a long way out, much further. I love this diagram. That sort of explains the whole thing you're looking at when you're looking at it straight on. The rings are in here. So these moons, these inner four, represent the outermost section of the ring system. And then there's Io, Europa, Ganymede, and Callisto, and then you've got the outer moons, if that makes sense. And Valetudo has a prograde motion, and one of these moons is going to collide with other moons, inevitably, which will be interesting for our fate, because everything that happens around Jupiter is tied to us in lots of ways, as we've seen in the past. So things can get dislodged, and I think Jupiter, being so massive, has an enormous impact. And who knows what would happen when two of those moons collide and one gets dislodged. Oh, I lose sleep over the near-Earth asteroids, let alone something like this. Who knows what could happen? Yeah, I think there's a lot that NASA doesn't tell us about. I bet there would be more. I think there are more. I'm not talking about UFOs. I just think there's more. There would be more near misses than we care to mention, or because it would cause panic, wouldn't it? I mean, imagine the effect on the world economy. People knew there was a rock heading for us, and they couldn't get it out of the way.
So are they prograde and retrograde, or
sorry?
Are they going around the same way?
The inner moons are.
The two that are going to collide.
Oh yes, they're going the right way. Yeah, Themisto and
So
Valetudo. Oh, they're not on the same orbital path. Right. There are two that are the two innermost ones are almost exactly on the same path. But because of the fact that all the moons are, tidally locked, they have the same face towards Jupiter too, they're locked in this resonance. I'll talk about that. So we don't have to worry about those inner ones. It's the outer ones, and those Valetudo and Themisto, I think, that are the ones that could be a problem. So the inner satellites are called the Amalthea group, and in order, they're Metis, Adrastea, Amalthea, and Thebe. They're really close to Jupiter, as you saw, inside the ring system, and they feed, two of them feed the rings. They, just like Stefan mentioned Io, but they also, I'll come to Io. Io is really exciting, a wonderful place, I reckon. These moons, along with the number of seen and as yet unseen moonlets, replenish and maintain the ring system. So those four inner ones up there that I just mentioned, do that. Then you've got next to them, you've got that main group of 4, Io, Europa, Ganymede, Callisto. And we'll talk a bit about those. But the inner moons are in this is a 1, 2, 4, the inner moons being the Galilean ones in particular, a 1, 2, 4 resonance. So I guess, correct me if I'm wrong, Stefan. So for example, Io will do 4 revolutions for 2 of Europa and 1 of Ganymede. And there's a diagram I'll show you, and you can see moments of conjunctions as they revolve about Jupiter. So models suggest they form by slow accretion in the low-density Jovian subnebula, which is the stuff around Jupiter when it was formed. A disk of the gas and dust that existed at its formation 10 million years in the case of Callisto. Now, subsurface, 3 of them have got subsurface water oceans, and of course, Io, unfortunately, has a magma ocean underneath it and is inhospitable. And there's a lovely diagram of what I was talking about with the ring system, the Gossamer rings, main ring, and those 4 innermost moons. So out here would be Io, Europa, Ganymede, Callisto. Gossamer ring, I don't know why it's called that. Do you know anything about that, Stefan? Gossamer ring, maybe it's so very thin, extremely thin. Anyway, let's move on. There it is. There's the orbital resonance that I was talking about. So 1, 2, 4. And you can see that when the lights flash, it's when they're in conjunction. So there's a conjunction, and so on. Io in the middle, Europa, and then Ganymede. Callisto is further out, and they reckon in maybe 1 billion years, Callisto will be in orbital resonance, and it'll be 1, 2, 4, 8. 1, 2, 4, 8. Yeah. I read that somewhere. I don't know if I've got it in my notes or whether I included it, all, but it was interesting to come across that. Now the irregular satellites, we won't spend too much. They're the groups. I won't dwell on these. They've just got their names. But Valetudo is the outermost prograde moon and is not part of a known family. Its orbit crosses paths with several moons that have retrograde orbits and may in the future collide with them. So Valetudo, for good reason, we could lose a bit of sleep over that one. Themisto is the innermost irregular moon and is not part of a known family either. So now the retrograde, they're the prograde satellites of the irregular ones, and then they've got the irregular retrograde orbits. So some of those outer moons that are in those red orbits, some of those irregular moons are actually prograde as well. They're not all retrograde. So that kind of breaks the rule, doesn't it? Interestingly. But, by the way, a lot of the names that have been used for Jovian moons have not so much the moons, but the features on them are Egyptian, which is really interesting. You know how they've got Greek and you've got Roman. Well, these are Egyptian, and I'll point some of those out to you later on. Ananke, just remember, Pasiphae is Greek, and Sinope. Anyway, a lot of them have lots of colours on them, red, where you can imagine that some of that would be stuff from Io, which ejects material out into space for hundreds of kilometres when there are volcanic eruptions. And they get caught up in the gravitational field, electromagnetic field around Jupiter, and I guess that stuff gets spread everywhere. But anyway, and it could be just native. Okay, so this is Galileo. Well, drawing of Galileo. And we're heading out to the Jovian system and the Voyager. You might recognise Voyager. There's Galileo. Anybody? It's hard to know the shape. Cassini, it's Cassini, and there is Juno. Juno's the three propeller blade thingy. And sorry, no, oh no, that's actually Juno. Oh, sorry. Oh, I'm not doing it in order. Sorry, I was just naming the spacecraft. But yes, Pioneer. Before that, Voyager. I didn't. A Pioneer, then Voyager, and then we had Galileo, which got burnt up. Cassini, Juno, Cassini, Galileo, Juno. I think something in that order. And that's New Horizons, which is the latest down the bottom there in the middle. So Voyager, New Horizons, Galileo, Cassini, and Juno. Just in that picture, just various spacecraft, but there have been others. So Voyager 1 and Voyager 2 did a flyby of Io and detected the presence of water on the surface of Europa. Now, Ulysses, I didn't know about Ulysses. Did you know about Ulysses? Has anyone heard of Ulysses? I had no idea. Anyway, it was this. Yes, it went around the sun, but it actually was able to explore the magnetosphere of yeah, Jupiter's a magnetosphere. And then Galileo, of course, arrived in 1995. Then the Cassini probe, which flew to Saturn in 2000. Then New Horizons, then Juno. So a lot of the Galilean moons have been now really well explored, photographically speaking. They did the same thing to, as you'll see, to Galileo that they did to Cassini, which is, well, with Galileo, they crashed it into Jupiter, and Cassini, as we know, they burnt up into Saturn's atmosphere for the reason that, for contamination reasons. But as I said in my last talk, I couldn't figure out the science behind that because the motors that they use have got radioactive particles in them, and they flew, Cassini flew through some of the ejected material from Enceladus, and so it would have contaminated that moon anyway. So to say, well, we're going to stop it from contaminating and then crash it into Saturn, kind of is like shutting the door after the horse is bolted. Anyway, I think the same thing was true of Galileo, maybe, because that went past Io and the material ejected there and the other planets. So the other moons. I mean, I don't know. Yeah. So any material being ejected would have been contaminated by the things have got radioactive particles in them. Sorry? It wasn't fear of radioactive. No, it was fear of microbial. But that would have happened. But that would have happened anyway. I mean, you could pick up stuff. Who knows what's out in space? I mean, we don't actually know. Yeah. From Earth it would. But what I'm saying is beyond that, I mean, what's out there? Yeah. I think there's too much. Yeah. But I'm thinking there's something between there and the systems they're exploring that could cause a problem. No. No. Anyway, with the mission extension, Juno has begun flybys of the Galilean moons, particularly Ganymede in 2021, Europa in 2022, and of course, a planned flyby of Io late this year. And once more next year, which is very exciting because the cameras on it are really fantastic. Now, Simon Marius Mayr, I'll just show you a picture. That's Galileo, and that's the German fellow Mayr. Now, apparently, it was virtually like something like a day apart that Galileo looked through his telescope and saw these moons and figured out that they weren't stars, that they were satellites of Jupiter, and that he saw them through his 2-inch, shockingly small, or was it 1.5-inch, dual convex and one concave lens telescope in a wooden tube. And Mayr, which I've got a picture of somewhere, that, and then one of those, and Mayr on the other side saw them and named them with his own mythological names. And yes, and then there was a big problem. So one of Galileo's telescopes, anyway, focal length of 1330 millimeters, 26 millimeter aperture. It's even smaller than I thought. Thought it was an inch and a half. It's an inch. It magnified 14 times, and an objective biconvex lens and a plano concave, plano one side flat and one side caved in. Now, sorry, I didn't mean to go backwards. Controversy. Poisonous reptile. That is what he called Mir, because apparently one of Mir's underlings was a guy who co-wrote a book on Jupiter and the Moon system, or I can't remember. I can't remember what the book was, but apparently material from it was plagiarised from work by Galileo. So this upset Galileo, and there was a big feud. And instead of supporting Galileo, because he wasn't in town, he said, "My student did that." The student, I forget his name. Peso, I can't remember the student's name. But anyway, the point is he accused him of plagiarism and not the student. And he called him a poisonous reptile, an enemy of all mankind. And then it only got worse, because then they argued about the nomenclature, who discovered what first, and the nomenclature of the moons. And Mir decided he would apply the names of nymphs and lovers of Jupiter. And so I'll just tell you a bit about that. Lovers of Jupiter, as you'll see in a moment. So each one of them, as we come to them, there's a little bit of a myth about them. But to combat that, Galileo, furious, decided to name them in order of their orbit. So 1, 2, 3, and 4. The moons became 1, 2, 3, and 4 in their distance from Jupiter. And he insisted on that being carried out, and he had something else. Oh, that's right. He was going to name them after the Medicis, his patrons. He was going to name them. This is typical of astronomers. If you want to crawl to somebody and get a bit of money, so you pay your patron, pay attention to your patrons. And he was going to give them names. I think, Cosimo Medici. I think so. Moon would be called Cosimo, and Matteo, whoever, But I think Mir had the right idea. Following the mythology was a much better idea, smarter idea. But anyway, we'll come to that. We'll look at the myths later on. So that's another replica of Galileo's telescope. There's a bit here about the order of discovery. I'm not going to go into that. But the moons gradually, one by one, from the turn of the century, were discovered. And then Voyager added its own bit by imaging space probes with Jupiter, 1979, 13 moons discovered, not including Themisto, which had been observed in 1975, and then was lost. And then in 2000 was rediscovered due to insufficient data initially. The Voyager spacecraft discovered an extra 3 moons, those inner ones that we talked about earlier. No additional moons were discovered until 2 decades later. Now, this is amazing. I won't go into all this, but these two guys, Scott Shepherd and David Jewett, seem to have discovered many of the moons of Jupiter using different telescopes. Quite famously. So you see their name everywhere here. All their observations still ongoing. So quite famous astronomers, having used a lot of the telescopes from the Atacama Desert. I think they used the Subaru telescope as well, which is in Mount Mauna Kea, and I've forgotten the others. But anyway, in collaboration, they seem to have discovered most of the moons in recent times. So, the Amalthea group. Prograde, circular orbits of low inclination. By the way, the names of some of these moons change according to the level of inclination. They end in O, they end in A, or they end in E, which was interesting. But anyway, these innermost ones, Jupiter 16, innermost moon, show you a picture of it. It orbits Jupiter in less than a day. And it is 60 by 40 by 34 kilometres, and isn't that a high resolution image? It's pretty small. It's just a blob of rock, basically. Not much to it. Tightly locked to Jupiter like all the other moons. And then you've got Adrastea, the next one out, discovered by Voyager 2. The other one was Voyager 1. Named after the Adrastea, foster mother of the Greek god of Zeus. So, in keeping with the mythology of the moons, they've used, Greek and Roman myth to use the Roman being the equivalent of Greek. Adrastea, foster mother of Greek god Zeus or Jupiter, the equivalent of Jupiter, orbits edge of the main ring and is thought to be the main contributive material to that ring. So again, what we mentioned earlier. And there's a picture of it. What an exciting, look at that. That's the small, 20 kilometres. So it's not very big. Now, Amalthea is getting on to a larger size as the third closest orbit and is with the fifth moon of Jupiter discovered and the fifth largest moon. So after Io, Europa, Ganymede, Callisto, you've got Amalthea. It's the next in size. Who discovered it? Edward Emerson Barnard, whom you might recognise as the guy who wrote everything about dark nebulae and was the discoverer of dark nebulae. And the Barnard catalogue was his. Barnard 33, the Horsehead, and so on. So now the surface of Amalthea is very red. They all would be red, you would think, because of material, the presence of sulfur, and that comes from Io. Maybe due to sulfur originating from Io, or some other non-ice material. Bright patches of less red tint appear on its major slopes. These are three pictures of it here. The one in the middle is the one that's a real colour, true colour, I think. And you can see it's actually quite red. So that's Jupiter 5. And that small writing says, pictures of, with a few little craters named, but we won't go into that. Now, Thebe. Thebe, of course, ancient Thebes. Remember ancient Thebes in Greece, Thebes city? It's named after a priestess of Thebes, Thebe, a priestess of Juno, Hera. The story about her. The mythology is wonderful. The fourth of Jupiter's moons, discovered by Synod. Now, I thought it was of Synod. And I thought, no, it can't be. Not Roger Synod, you know, the one who does all the maps. You've not heard of Synod? Synod, yes, if you know star atlases, Synod's quite famous. So I looked him up. No, he's a part of the Voyager team, original Voyager team. Officially named after nymph Thebe, second largest of the inner moons. Anyway, it's located on the outer edge of the Thebe-Gossamer ring, formed from the dust ejected from its surface. Anyway, thought like Amalthea to consist of porous water ice with unknown amounts of other materials. And that's 116 kilometres, so it's getting a bit bigger. But still, they are very small moons. The Galilean moons of Jupiter. Can you all name those? Yeah, we all recognise them. Io, Europa, Ganymede, and Callisto in that order. And if you look at Ganymede, it's the biggest moon in the solar system. Bigger than Titan, which is number 2. With a sizable diameter. And Callisto is not far behind. And in fact, I think Callisto is still bigger than Mercury, or the same size as Mercury, the one on the right. Ganymede is bigger than that. And even Io and Europa are bigger than our moon in diameter, which is quite substantial. So you can see they're, the most readily visible things you can see with the naked eye through a telescope or binoculars. You don't have to strain to see the moons. The largest of the four is Ganymede, Ganymede and Callisto, both of which are either large or almost as large as Mercury. They're not as massive. The smaller ones, about the size of the moon, the three inner ones are in a 421 orbital resonance, which we talked about earlier. Anyway, the names that have persisted of these moons were the ones given by Simon Marius or Simon Mayer, the German I told you about, who discovered them independently from Galileo. He named them at the suggestion of Kepler, the famous astronomer, after the lovers of the god Zeus, the Greek equivalent of the Jupiter, in his Mundus Jovialis, published in 1614. Galileo refused to use Marius's names and invented as a result the numbering scheme that's still used today nowadays. So Galileo had the last laugh. Well, sort of, because we still use the numbering system as well, in parallel with their proper names, so they both coexist. All right. And there's the last picture of their comparative sizes and a bit of data. So even Io, 3,660 kilometres is quite big, compared to Pluto's about 2,700 or 800 or something, or a bit more. It's not far off it, but it's still bigger than Pluto. which surprised me. I didn't know that. Anyway, they're they've got little diagrams there of the inner structure of the moons, and their orbital period, relative to Io. But anyway, we'll leave that. You won't worry too much about it because we're going to deal with those in a moment. The moons are the same age as the rest of the solar system, roughly, about 4.5 billion years. Now, music. So, sorry, but that's going on a bit long. We're going to deal with Io, and the music's supposed to stop. Oh, it has, thank goodness. I mistimed that one. Now, Io, it does look like a pizza, does it not? Or a very bad orange, as some call it. Spectacular colours, most volcanically active thing in the whole solar system, world in the solar system. Hundreds of volcanoes, over 400, and some erupting, as we know, plumes several hundred kilometres high. Io's extreme geological activity is a result of tidal heating. Now, as a result of two things mainly, it's not just Jupiter's pull, but also the pull of the other Galilean moons. So it's a tug of war. So its surface, now I read, this is astonishing. Its surface rises by 100 metres. Now we've got Earth's tides. They can rise by, that's water, and that rises by 10 metres. Well, this is a crust, and it rises by 100 metres. Yeah. Yes. But, yeah. I think that's astonishing. That's a lot of pulling power from the planet, other moons. So it always points the same side toward Jupiter in its orbit around the planet. The large moons perturb Io's orbit into an irregular elliptical one. So it has widely varying distances from Jupiter and subjected to tremendous tidal forces which cause it to bulge up and down as much as 100 metres. And compare that to Earth's, 18 metres, the tides on Earth. Fourth largest in the system and more than 100 mountains, some of which are taller than Earth's Mount Everest. Unlike most satellites in the outer system, which have a thick coating of ice, Io is primarily composed of silicate rocks surrounding a molten iron or iron sulfide core. Now, it has an extremely thin atmosphere made up of sulfur dioxide. If a surface or collection vessel would land on Io, it would have to have a tank-like body, like those Soviet Venera probes that didn't land, the ones that landed on Venus, which subject them to 90 Earth atmospheres and tremendous heat, 500 degrees Fahrenheit or something. I can't remember the temperatures, but it was pretty high to survive. But in this case, to survive the radiation magnetic field, they'd also need retro rockets. You can't parachute down; there's no atmosphere. So you'd have to sort of no atmosphere talk. You'd have to descend by very careful use of rocket power to the surface. Now this is actually, if I can get this to move, I think I'd have to use my mouse on that. No? Oh, it didn't work. You could actually rotate that. It was a 3D rotator, and it was really good. But anyway, volcanic eruption. Io receives, now I can't tell, I don't know. I don't know the units here. Maybe you could explain these, Stefan. Io receives about 3,600 rem of ionising radiation. I don't know what rem stands for. If anyone can help me. But anyway, a lot of radiation from Jupiter with which it interacts, as we'll see. Look at that beautiful composite mosaic. Now there's a picture. Voyager 1 mosaic shows Io's south polar region near the terminator right centre. A couple of mountains, 10-kilometre high mountain down the bottom there. The composition of the volcanic plains of Io, mainly sulphur with a coating of sulphur dioxide, which of course if the sulfur that goes up and comes, as sulfur dioxide is expelled, it comes down and freezes onto the surface. So you get a kind of smoothing over. So you can't have craters lasting on Io because the surface is constantly changing with all the volcanic eruptions and the lava flows. So anyway, so you've got sublimation of sulfur, and then you've got the sulfur dioxide, and then you've got it freezing over again on the surface. You've got hot stuff and cold stuff juxtaposed. The lovely story. One of Jupiter's lovers, poor little Io. Jupiter took a fancy to her, disguised her as a heifer. So the story goes. So his wife Hera wouldn't know. Fell in love with her, she being immortal. Anyway, so Hera found out, and she, I forgot, what did she do? Anyway, the story goes that he tried to disguise her, it didn't work, and she punished her by having a Argus watch over her, the guy with 100 eyes. Jupiter didn't like this, so he sent Hermes, the god, the Mercury, the messenger god Hermes, the Greek name Hermes, to play the panpipes and distract Hera, and distract him, Argus rather, from watching over her so he could steal her away. And she wandered away, and then Hera found out, and then she sent gadflies, you know, those flies that annoy cattle, to pester her because she's a heifer, still a heifer. Anyway, she wanders over to the Bosporus and finally finds Prometheus, who says, "You'll be okay, don't worry, just head towards Egypt," or wherever. She goes towards Egypt, and she turns into a more human being again, and then Zeus is in love with her again, and so the story goes. But anyway, these things are fascinating to read. Anyway, so there's a lot of interaction between Io and Jupiter. So let's just quickly have a look at it. Look at that. Now that's one of those calderas. You know, in a volcano you've got a caldera. So when it collapses, this is what you've got, a lava lake in the middle of it. An enhanced colour composite, deposits of sulfur dioxide appear in white on the right there, and grey hues. The yellowish and brownish hues are the sulphurous materials. Bright red materials such as the prominent ring around Pele and black spots. Pele is this volcano. Oh, that's interesting. That's not working tonight. Oh, sorry. Oh, that's a turnout. Sorry. Back again. I beg your pardon. I don't know what's happened there. Anyway, so there's Pele. Gigantic. And these are the points of eruption. Now, I've got a picture of one of those shortly. Patera. Patera just means like the caldera, the basin where the lava is collected. The image shows results of lava interacting with sulfur-rich materials. So that's Tupan Patera, named after a Brazilian thunder god. I wonder if Pele was named after the soccer player. Don't know. Sorry. Anyway, image width is 100 kilometres, so that's quite imagine. Wow, that's massive. What an inhospitable moon. And there's the interaction with Jupiter. Isn't that astonishing? So, the Jovian magnetosphere, showing the Io plasma torus in red. So all of this around here is in red. The neutral sodium immediately surrounding Io. So there is yellow. The Io flux tube. So all the particles are like travelling in a electromagnetic field, which is shaped like a tube, I suppose, which is a flux tube in green, but following the magnetic field lines of Jupiter, and the magnetic field lines in blue, the general from Jupiter. So no wonder poor old Io is unstable with all that going on. And not to mention the other moons, which will be well within the magnetic field lines of Jupiter, although, albeit out here, they'd be weaker than obviously closer. So Io plays a significant role in shaping Jupiter's magnetic field. I love this. Acting as an electric generator that can develop 400,000 volts across itself and create an electric current of 3 million amps, releasing ions that give Jupiter a magnetic field inflated to more than twice the size it would otherwise have. So Io is a generator, kind of a generator. The magnetosphere of Jupiter sweeps up gases and dust from Io's thin atmosphere at a rate of a tonne per second. This material is mostly composed of atomic sulfur, oxygen, and chlorine, sodium and potassium, as well as molecular sulfur dioxide. Anyway, most of this stuff comes from Io's atmosphere. The materials, depending on their state and composition, end up in various non-ionized clouds and radiation belts in Jupiter's magnetosphere. So a lot of interaction going on there. And for those of you, a flux tube, I looked it up. The electrodynamical interaction between Io and the Jovian magnetosphere results in an electric circuit, which we just read about, that runs, electric circuit that runs from Io along Jupiter's magnetic field lines and closes through the Jovian atmosphere through the poles. As you can see, that's this thing here, going north and south, through the north and south pole. That's the Io flux tube.
Do the same thing with a star in the middle.
Yeah.
And a planet.
Oh.
Related to Io, there's radio bursts, regular radio bursts.
Oh, okay. Yeah.
So Jupiter is one of the brightest radio sources.
Yeah. Oh.
That's a neat and another way of finding the exoplanets.
Right. Oh, I didn't know that. I've been enlightened. Thanks. Thanks, Stefan. That's good. So, anyway, because there are no craters, they can't exactly determine the age of Io like they could other bodies, because the craters are all disappeared, what ones there were. So it's been compared to a rotten orange or a pizza because its surface has been constantly recovered. I just love that landscape. What a landscape. It does look like a rotten orange, come to think of it. Something that's gone mouldy anyway. And then down here, you've got Pele, and that's the caldera of Pele. And you've got, some of these were erupting in, I think I've got a photo somewhere here. Yeah, the eruption of Pele. So that's it up there. I wonder why that thing isn't working. The volcanic plume, 300 kilometres up into space. And there are some more interesting things of the layout of the, you can get maps and all sorts of things on Io. It's been everything's been labelled. But a lot of the names, as I said to you, are usually they're named after Egyptian things, or in this case, Norse mythology, and a combination like, there. Oh, maybe I should turn that off. Hang on. Just had a thought. No, made no difference. So up the top there, you've got Tavashtar, Thor, Norse mythology, different names. Shamash, so some are Indian, and a combination. Annotated image of Io showing major eruption centres. Let's move on. That's just a diagram of the core, iron and sulfide. I won't dwell on that. And here is the story of Io, Europa. Sorry, we've moved past. Have we gone past Europa? Hang on. Have I missed a slide? Let's go back. Did I miss Europa? I've got the slide in the wrong place, I think. Yes, I have. I put the slide in the wrong place. Never mind. We'll come to that shortly. That's the picture on the left there should belong to Europa, not here. Again, someone disguised as something else. That's the story of mythology. Finally, some pictures by Juno of eruptions on Io. Incredible. What a violent surface. And there are two pictures. The one on the left, see the white? That's been burnt out. It was so bright it burnt out on the image. Such a violent eruption. And there's an actual live set of stacked images of a volcanic eruption. Look how big that is relative to the planet. Imagine if we had a volcanic eruption that was as violent and as big as that. Anyway, New Horizons. March the 1st took this picture of Tavashta Patarai, which was on that map earlier. Huge, absolutely, 330 kilometres high. I'll speed up. Finally, the mountains of Io, lots of mountains. There are 100 to 150, some rising, average of 6 kilometres in height. I think the longest one was, a maximum of 17 and a half, 19 maybe kilometres high, which is a hugely high mountain. That's a great height. What's Everest? 30,000 feet, 6 miles, maybe 10 k's. So twice the height of Everest. Quite substantial. I like artists' renditions of things. This looks like a chemistry set, doesn't it, in the middle here? Yellow. And, oh, I used to love sulfur because I used to make my own gunpowder. So I used to collect sulfur. I love looking at it in canisters. It's a wonderful thing. We'll move on quickly because the other moons you'll be relieved to know are a bit shorter than this. I just spent a lot of time on Io. I was besotted with it. Now, it does have an extremely thin atmosphere of sulfur dioxide, but gas in Io's atmosphere is stripped by Jupiter's magnetosphere, as we saw. So it's got a very thin atmosphere, and what it has is got sulfur dioxide, and the plumes of sulfur dioxide, 10,000, that's 1,000 tons of sulfur dioxide per second go up into Io's atmosphere. That's huge, isn't it? Though most of this condenses back onto the surface, which is ironic. So it goes up hot, comes down freezing cold. Much of the sulfur dioxide in the atmosphere is sustained by sunlight-driven sublimation. So sulfur dioxide on the surface sublimates from solid to gas in one go. Various researchers have proposed the atmosphere of Io freezes onto the surface when it passes into the shadow of Jupiter. Very interesting. Moving on. How are we going for time? All right. Last thing. Newsflash. The James Webb Telescope and the Hubble Telescope are set to team up and observe Io, which you're going to do. This is only last week or something. The two space telescopes will remotely collect data about the world, and then that information will be put into NASA's Juno spacecraft, put to use by Juno spacecraft. More specifically, the data will help guide Juno during future flybys of Io. So there's an exciting development, especially when you've got the James Webb operating. It'll be fantastic. I love those artists' interpretation. Do you ever, when you see these pictures, you ever think, imagine yourself on the surface of some of these moons? The view of Jupiter would be absolutely incredible, no matter which one you're on. I think they'll find life on this planet, I reckon. I reckon this is a better candidate even than Enceladus, Saturn's Enceladus. It's just got so much going for it in terms of its ocean. We know it's got an ocean. The smallest of the four Galilean moons, smallest of the four Galilean moons orbiting Jupiter, and the sixth closest of all the 65 known. It is the sixth largest moon in the solar system, named by Simon Marius after the Phoenician mother of King Minos of Crete. Now, King Minos of Crete had the Minotaur. Remember the Minotaur? You heard of the Minotaur, Minos? Yeah. Anyway, and lover of Zeus, of course, they all were. Physical characteristics, just a few points. Orbits Jupiter every 3.5 days. Similar in composition to terrestrial planets, being primarily composed of silicate rock. An outer layer of water about 100 kilometres thick. That's amazing. Recent magnetic field data from Galileo established that. I don't know how they do it, but they can tell whether the thing is a water world by using this sort of, looking at the magnetosphere around a moon or a planet. And they use spectroscopy as well, I guess, and work out that it's got an ocean underneath it. Anyway, it's likely to be a salty ocean. A tenuous atmosphere of oxygen, so very little. With the arrival of the telescope, scientists were able to examine the surface of Europa more closely. Two new studies using a technique called near-infrared spectroscopy will assess the concentration of carbon dioxide at the surface and trace where it came from. Together, the results suggest carbon on Europa likely originates within its ocean. So there is definitely evidence of an ocean, and Cassini established that as well. I'm skipping through this because we're running out of time. The model I think scientists prefer is the bottom one on the right, rather than the top one with convective ice. It's more like an ocean under the ice. Unlike Earth, magnesium sulfate might be a major salt component of Europa's water ice. Big trouble. Why? Magnesium, milk of magnesia, Epsom salts, is an emetic, an anti-diarrhea, a thing that causes diarrhea. Don't drink the water from Europe. Anyway. Oh dear, sorry, I can't help. I love jokes like that. When I was an air cadet, can I digress for a moment? When I was an air cadet, some air cadet put Epsom salts in the tea or coffee urn. And when we were in the mess one night, and he put a 1 pound bag, 500 gram bag of this into this big tea urn. And the cadets who had the last of the tea for the night, and I was one of them, we got back to our barracks and we all sat upright at about 8 o'clock and rushed to the toilet block. And we all had an attack of diarrhea at the same time. It was like clockwork. And the toilet booths were 20 deep with people waiting to get in. It was shocking. Needless to say, said cadet was expelled. It wasn't really funny at the time, but looking back on it, it was funny. But Epsom salts is not my friend, not anybody's friend. Although it's good to, apparently, for what is it? Like a massaging, like a relaxant. Anyway, recent observations from Hubble, as well as analysis from Galileo data, have suggested it is possible that thin plumes of water are being injected at 160 kilometres above Europa's surface. So there is evidence of this water ocean, definitely. I'm skipping through this quickly. Yes, a thin one. It's got a thin one of oxygen. But you see, that could be, there'd be chemical reactions from the water. I don't know what chemical process could be happening. Chemical processes could be happening. Sorry?
High energy particles coming in, breaking the water molecules up, and hydrogen.
There you go, separating hydrogen and oxygen. Yeah. Well. Oh, right. No. So there's a mosaic. Now look at all the lines. So we call those lines linei, and we'll come to that in a moment. Studies of Voyager and Galileo images have revealed evidence of subduction on Europa's surface. Now, a bit of explanation there for those who've done geology. So you know how we've got the Earth is on plates? Continents are continental plates. They all drift around, right? So at the edges, say, of South America, the oceanic plate, the South Pacific plate, is subducted. So it's drawn and sucked under the continent of South America. And now our professor of geology, Warren Carey, is a wonderful teacher. He was the first guy to talk about this in his PhD thesis in 1930. And his supervisor told him, don't put it in because no one will blame. No, but he talked about plate tectonics. And in fact, he insisted on, whenever you did exams, you had to write about plate tectonics. But it was proven to be the case that that's true. So the mid-Atlantic ridge is where you tear things apart, where the crust is torn apart. And so you get volcanic activity there, or orogenic, you might get lava coming out. Hence the mid-Atlantic ridge is a mountain chain going through the middle of the ocean. And then on the edges, the subduction means to lead under. So it's been taken underneath the crust. It's amazing. So what's causing that? Huge convection currents in the Earth's mantle. So all of those things about plate tectonics apply, they reckon, to this moon. It's doing the same thing. So that's what tectonic plates are, just the bottom bit there I'll just explain. So anyway, striking, these lines are called linei, hence line. Close examination shows that the edges of its crust on either side of the cracks have moved relative to each other, which suggests movement of the crust. The larger bands are more than 20 kilometres across, often with dark diffuse outer ridges, regular striations, and a central band of lighter material. The most likely hypothesis is that the lineae on Europa were produced by a series of eruptions of warm ice as Europa's crust slowly spread open to expose warmer layers beneath. This effect would have been like that seen on Earth's oceanic ridges, which I was just talking about. So there's tension, there's that lateral tension, then there's subduction and plates moving and colliding. And we're going to, I think I've got a picture here somewhere. There it is. Now that top one is subduction. See how that's that seems to have gone under? Yeah, that kind of thing is at play here. One of the plates is seen as a flat lineae there in the upper portion of the image. I won't read all those notes. And a beautiful picture of the lineae, the lines. So they're like, it's almost like having flat icebergs crunching into each other. Like tearing on one part and then compression. So you've got tension and compression working together like you do in our plate tectonics. Same sort of thing. 6-frame mosaic. The X is 75 by 100 kilometres, where the icy crust of Europa has been disrupted by activity from below. So those currents that we talked about, the warm stuff rising up in the ocean, which is probably heated by a hotter core, causing the ocean, causing currents which then tear the crust, move the crust. Anyway, there are pits and domes as well, which range from a few kilometres to nearly 20 kilometres across. Amazing. I just wanted to show, isn't that a beautiful picture? Colour pictures obtained on the 6th of September, and you can see, by Galileo, and you can see the this material. This is fascinating. All that stuff. You know, that's something from within the ocean maybe that's come up through the crust and come out onto the ice. Or it might be stuff that's landing there anyway, courtesy of Io. Small ridges, bands, rounded domes, disrupted spaces. We call this area here chaos terrain. So that's because there's no sort of smoothness about it, or that. Yeah. Chaos transition, crisscrossing bands. Yeah. Fascinating moon. This will be a really wonderful place to visit, as long as you're not near a place where it's venting water. Anyway, they've detected water vapour for the first time on Europa's surface, so that'll be one of the places that we'll have to spend some time on it, and the atmosphere of oxygen as well, which is interesting. Now, they'll sample it in the same way that Cassini sampled Enceladus's vapour. It went through the plumes, so they'll use the same principle again, hopefully. Future missions to Europa. Without dwelling too long on it, JUICE, the guy in the paper today, he's part of that mission, the JUICE mission, which is Jupiter IC, Moon's Explorer, launched in April of this year, and NASA's Europa Clipper will be launched next year. While JUICE will observe Europa, Ganymede and Callisto, the Europa Clipper mission is planned to make 45 flybys of Europa, maybe even soaring through its water plumes. Though NASA has stated Europa Clipper is not a life detection mission, it probably will be. The spacecraft will attempt to identify locations beneath its crust that could hypothetically support life. And NASA was considering sending a lander. Here's a little picture of it, but it's died, that mission. So it's not going to happen. So there won't be a lander, unfortunately. The Europa lander, launched from GMO, Jupiter, it's the same as JUICE spacecraft, Jupiter Io mission, no, I forget what that's called now, and dropped on Europa's surface. The spacecraft going around Europa and then landing on the surface. I forget what GMO meant. Sorry, it was an acronym for something, but I don't know what. This is an amazing moon. Now, I haven't got 10,000 slides on this, so don't worry, there are only a few. But Ganymede has got a lot of interesting things on it. Look at the huge crater impacts, the largest solar system moon by bar none, Like Titan, is larger than Mercury, but has a somewhat less surface gravity than Mercury, Io, or the Moon. Its magnetic field, discovered, made by the Galileo spacecraft, causes auroras, which we all know what auroras are. Anyway, because Ganymede is close to Jupiter, its magnetic field is embedded in or lies within Jupiter's as well. When Jupiter's magnetic field changes, the auroras on Ganymede also change, rocking back and forth. And there's a picture of the sort of talk about auroral photography, Dallas. We could have fun on. We could certainly have fun on this moon. That'd be amazing. Hubble images of Ganymede's auroral belts. The amount of rock in the moon's magnetic field suggests the moon has a subsurface saltwater ocean. Moon number 3 with a saltwater ocean. Boy, are they going to have a time out there exploring these in the next 50 to 100 years. By the way, of the 4 Galilean moons, this one is named after a guy, not a gal. And Jupiter took a fancy to this guy. A beautiful young boy who was carried by Olympus to Olympus by Zeus, disguised as an eagle. So this time Zeus is always disguised as an eagle. Ganymede became the cupbearer of the Olympian gods. After that, I suppose he had no choice. He was a prisoner. Anyway, a beautiful picture of it in front of. Wouldn't you? You'd kill for a picture like that through a telescope, wouldn't you? You know, imagine seeing that. It's just gorgeous. The colours, a purple hue. So slightly more massive than the second most massive moon of Saturn, Titan. Orbits at 1 million kilometres. So that's a substantial distance. Anyway, we talked about the resonance before that, and the fact that Ganymede is tidally locked, meaning that like Earth's moon, the same side of Ganymede always faces Jupiter. And the other 3 Galilean moons are, of course, also tidally locked. Anyway, beautiful pictures. So there's an example of that resonance we were talking about earlier. Laplace resonance of Ganymede, Europa, and Io. We are close to finishing. A couple of things about Ganymede's structure. 3 layers, metallic iron core, spherical shell of rock, and mostly ice, but also a suspected saltwater ocean in between, underneath the crust. It may have a stack of several ocean layers separated by different layers of ice as well. Extreme depths involved, about 800 kilometres to the rocky seafloor, means that temperatures at the bottom of the convective ocean can be up to 40 K higher than those at the ice water interface. That's amazing. Yeah. Anyway, in March of 2015, scientists report that measurements with the Hubble telescope of the aurora how the aurora moved, confirmed that Ganymede has a subsurface ocean. We'll leave that. It makes it a place that could be habitable. Another picture of it. The crater, what's it called? Tashmetum. Prominent rays are at the lower right, and the large ejector field of Herschel at upper right. Part of Nicholson Regio is at lower left, bounded to its upper right by Harpagia sulcus. Sulcus is Latin for a ditch or a furrow, or a place of lower elevation. Again, a tenuous oxygen atmosphere has been detected. Daytime surface temperatures from minus 297 to a balmy minus 171 degrees. Jupiter and its moons receive less than 1/30 of the amount of sunlight that the Earth does, and Ganymede doesn't have a dense enough atmosphere to trap heat. So anyway, there is an oxygen atmosphere. So, and there are a couple of interesting impact craters. Close up of the dark side of Ganymede by Juno in June of 2021. But not so heavily cratered, nothing like the next moon, Callisto. I think a picture of the aurorae and that crater that we talked about before. I shall move on from here. Tros crater, taken by Juno. So, like the other moons, it has its own magnetosphere. That is a picture of Zeus taking away, abducting Ganymede, the young lad. And there's an interesting look at that terrain. That Regio we looked at before, Nicholson Regio, and the sulcus is that area here. Oh, I think that's also the term for the furrows in the brain, those deep furrows are called sulci. I think that's the same name they use in physiology. Anyway, the troughs that dominate the surface of Ganymede may have been caused by a collision with a massive object, a 150 kilometre radius impactor, so they think. But the terrain doesn't look uniform by any means, does it? Some interesting geology there. It's images by Juno. Future missions, JUICE, which we talked about earlier, will be the first to enter orbit around Ganymede. It was launched on 14th of April this year. It's intended to perform its first flyby of Ganymede in 2031. It's a long way off. And then enter orbit of the moon in 2032. When the spacecraft consumes its propellant, JUICE is planned to be deorbited and impact Ganymede in February. Another impact. There's going to be a lot of stuff out there in February 2034. In addition to JUICE, of course, there's the Europa Clipper we talked about earlier. We'll conduct 4 close flybys of the moon. Okay. Last one. This is short. Sorry, I've gone on a bit long. It's an hour already. Okay, Callisto. Look at Callisto. It is the most bombarded place you've ever seen. It makes Mercury look smooth. Second largest moon of Jupiter, a really big moon. Some scientists thought of Callisto as a boring, ugly duck moon and a hunk of rock and ice. That's because the crater-covered world didn't seem to have much going on. No active volcanoes, shifting tectonic plates. But from NASA's Galileo spacecraft, it revealed that Callisto may have a secret, a salty ocean beneath its surface. Number 3 with a salty ocean. That finding put the once seemingly dead moon on the list of worlds that could possibly harbour life. Callisto is there on the left, a priestess of Hera, and that is Diana, or Artemis, the goddess Artemis, sitting down there. Callisto is named after one of Zeus's many lovers or sexual partners in Greek mythology. She was a nymph who was associated with the goddess of the hunt, Artemis. Anyway, all these paintings you've seen are from Pompeii, but from a house that I've never been to, the house of, it's the same house, the house of Jason and something else, I think. That little guy there is Eros, god of love. Anyway, this moon orbits at a distance of 1.8 million kilometres, which is a huge distance. According to Greek mythology, Callisto was a nymph and a follower of Artemis. In fact, I think she was a priestess of Artemis. Zeus developed an attraction to her and turned himself into Artemis to lure her. So he was pretty handy with disguises, old Jupiter, wasn't he? After Callisto became pregnant, she was expelled from Artemis's hunting group. Once Hera found out, she turned Callisto into a bear. So, anyway. Now, I love this picture for one reason. If you look at it, beautiful painting, I think 17th century, 18th century, I forget who did it. Oh, no, it wasn't. Hang on. Who was it? Carol Phillips Spilnix, maybe more contemporary, I'm not sure. But if you look here, you can see her, Callisto, with Jupiter. And then over here, you can see her being dragged by her hair. And that's Hera dragging her away. So, not very nice. Okay. Surrounded by a thin atmosphere of carbon dioxide. Again, coming back to the water idea. Probably molecular oxygen as well as by rather an intense ionosphere. It orbits at that distance we mentioned, and it takes about 17 Earth days to complete an orbit. It's tidally locked like all the other moons. The surface of the Callisto is the oldest and most heavily cratered. It does not show any signs of subsurface processes, plate tectonics, volcanism, none of those things, no geological activity, and is thought to have evolved under the influence of impacts. Now, there are some multi-ring structures, huge impacts. I don't know if you've seen them. There are 2 we're going to talk about, or just mentioned to you. One is called Valhalla. Again, going back to Norse mythology. Oh, hang on here. There's a picture of the Galilean moons. I don't know why I had that in there. Callisto is the outermost of the 4 moons. Yeah. It hasn't got. Callisto does not expect it to be captured into this pattern in about 1.5 billion years, completing that 1248 chain that I mentioned earlier. And finally, charged particle flux from Jupiter's magnetosphere at its surface is relatively low, 300 times lower than that at Europa, because it's further out. Unlike other Galilean moons, charged particle radiation has had a relatively minor effect on its surface. So anyway. So it's of all those moons, it's certainly the quietest in terms of activity. Carbon dioxide, silicates, organic compounds have been discovered. There is that massive impact site. Pretty obvious that it was huge, but it's kind of eroded. It's sunk. So if you have ice and it sublimates and you've got all this material, it eventually, whatever you had there starts to sink. There's no wind to take it away. There's no Aeolian process like we have on Earth. There's no atmosphere to talk about really. And so gradually this stuff just withers away. And that's what they've found. They reckon that there's a subsurface ocean of water, yes, but things like this are starting to weather away as if they've been eroded, completely eroded. 3,800 kilometres in diameter. That's enormous. Last slide's coming up. The core looks like that. Model of Callisto structure, ice layer, possible liquid water layer, and an interior rock layer. Okay, I think I've mentioned all those other things. The salty ocean could be 150 to 200 kilometres deep. When you think of the Earth, you think of the depth of those oceans, it's vastly, vastly greater. Last bit, surface features. Light plains, cratered plains, smooth and dark areas, multi-ring structures. Now, I was talking about things collapsing. So if you look on the right, that landscape, that's what it looked like originally. That's what it becomes. So material out of these little, they called them spires. Material or spires or something else. Spires, I forget the other term they use, but there are spires, and those spires, stuff might have been thrown out, ejected, froze in place, but the ice sublimates and the dust that's there sinks. So you get a kind of erosion. All the surface features become smooth like that over time. So it's got its own built-in sort of disintegration process. What were they called? Icy knobs or spires, possibly formed from the ejecta of an ancient impact, which contained darker dust that has slid down as the ice erodes even further, and the spires eventually disappear, leaving craters exposed, as we can see in that lower image. The smallest features you can see are about 3 metres across. The areas captured in the images lie south of Callisto's huge Asgard impact basin. The other one was Valhalla. So I think I've got a picture near Asgard. What do you notice here? If you look here, oh, there's the arrow. That's a crater, but it's a dome crater. So this is a normal crater like you see on the moon, but this is a dome crater. And they reckon that's because the material under it's suggesting the presence of water and a slushier surface, and it's risen up, maybe from convection or something else, and caused that unusual shape. This is Har with a central dome. I don't know what the origin of. Tinder sounds like Norwegian, doesn't it? T-I-N-D-R. Anyway, Valhalla and Asgard are the two big formations on the impact craters or impact areas, thousands of kilometres across. A small number of very large, more than 100 kilometres in diameter, and bright impact craters show dome geometry like the one I just showed you. These are unusually shallow and may be a transitional landform to the multi-ring structures as with Loifu impact feature. But, anyway. they don't know enough about them. So I have to land there, I guess. Now, if you look here and you look there at the bottom, you'll see there's been landslides. And those two craters on the right edge, and they reckon the material just after a while does the same thing we saw on those ridges. It slips, but through sublimation processes. Two landslides, 3.5 kilometres long, visible on the right sides of the floors of the two large craters. They occurred when material from the crater wall failed under the influence of gravity, perhaps aided by seismic disturbances as well. But anyway, so they reckon there's some sublimation of water or other volatiles from the dirty ice in the bedrock, which causes decomposition. The non-ice remnants from the debris avalanches descending from the slopes descends the slopes of the crater walls. And the knobs we saw, or spires, are thought to represent remnants of crater rims degraded by as yet uncertain processes. Anyway. And you can see there, look, that's what was originally, and that's what is. You know, eventually it all just withers away. That's a magnified view of it. But you can see those craters are gradually disappearing, which is interesting. Again, to do with the sublimation process and maybe some quakes, who knows. And we're near the end now. A couple of beautiful pictures. This is Asgard. Remember I told you the two big impact? On the right is Valhalla, on the left is, this is from Asgard. One of the largest on Callisto, the Asgard multi-ring structure, located about 30 degrees, The Asgard structure is 1,700 kilometres across and consists of that bright central zone surrounded by discontinuous rings, degraded rings that are disappearing. Anyway, we won't deal with the rest of that because we're running out of time. So I will finish up. One last pic. Look at the surface. Look how it's like someone's just scrubbed it. And those surface features are disappearing, the craters, the pock marks. So you can see that process. So even though it's not volcanically active or active in other ways, those craters are gradually eroding under sublimation processes and things we don't quite fully understand. Some sort of degradation processes. And that's a massive scarp, as you can see, raised area. One of the many features inside Valhalla, you know, the rings that we saw? That's just one of them. Now, a portion of the chain of impact craters is seen in the image taken by Galileo. This crater chain is believed to result from the impact of a split object like the fragments of comet Shoemaker-Levy, which smashed into Jupiter in 1994. So I think this is the second last one. Is there life on Callisto? Well, halophiles, those things that thrive in our oceans on salt water and in extreme pressure and temperature, might exist. As with Europa and Ganymede, the idea has been raised that habitable conditions and even extraterrestrial microbial life may exist in the salty oceans under Callisto. The principal reasons, however, the environmental conditions necessary for life appear to be less favourable on Callisto than on Europa, and the reasons for that are the lack of contact with rocky material and the lower heat from the interior of Callisto. Callisto's ocean is heated only by radioactive decay, while Europa's is heated by tidal energy because it's closer to Jupiter. It is thought that all of Jupiter's moons, of all its moons, Europa has the greatest chance of supporting microbial life, and there are the missions that are future missions that are coming up. JUICE, April the 14th, which you know about, the Europa Clipper, and China's Tianwen-4 is planned to launch to Jupiter around 2030. Isn't it amazing how China has advanced now and caught up? It's doing an amazing job. And there's a picture of the JUICE mission, like a double, two sets of solar panels, Jupiter Icy Moons Explorer. And that guy we saw in the paper today could probably tell us a lot about that. Potential habitation. I won't dwell on that. That's just a fanciful thing. I won't show you that. It's a beautiful video. We haven't got time. There's all sorts of stuff on these. Shadow of Io and Europa. I'm sorry I raced through this. Meanwhile, back on Earth. Oh, what a cute little Siamese. Is he friendly? Look at the... I wanted to bring a cat thing in. So that's it, folks. I'm sorry I've raced through that. There is so much there. Very interesting material on those moons. There's beautiful videos. And if you go into NASA's site, you can find so much stuff. You could spend years going through it. And the images are glorious, like that lovely one of Io and Europa in front of Jupiter. I've got a whole lot of these things. I never get tired of Gary Larson. Have you ever seen pictures of him? He's quite a young guy. Yes. Yeah. It's an ice crust by appearances. Any sort of, well, the silica materials that are inside the moon rather than on its surface, I think it's mostly just ice. And it probably just moves like plates, you know, which is plausible. It'd be a fantastic moon to visit. Europa would be my pick. Well, yeah, with the methane. Yeah. You've got to wear stuff there. Europa, yeah, you wear your space suit. But mind you, you've got to be wary, because if there are any geezers of water, you can hear them. If you feel a rumbling, you better move to higher ground. Anyway, thanks, folks. So let's have a break. And the other thing's just a quick thing on the night sky for September. Yeah, boy, I think it's time to have a some exotica. We're missing some.
Yeah, I've already gone through it. Thank you, though.
All right, just a quick thing. Yes. A quick thing on the September sky, which I was going to do last. It's out of date, but all you've got to do is allow for a couple of hours of rotation. So what you see is rising 2 hours earlier now compared to what I've got on there. That's basically it. I was saying earlier I'm going to make up a song called the Mount Pleasant Blues. And it's going to feature party pies, wind and other things in the lyrics. And I'll have to get someone who's musical to put it to music because of our experiences of observing. Now, I hope this works. Well, that's a nice picture, isn't it? Is that by Miguel? Miguel Claro. Sorry. So looking north, look, it's much the same as it is now. So what you see is Libra's down here setting a course of Ficus, Scorpius above with Sagittarius above the ecliptic there, just out of sight. But anyway, so a couple of things to notice. A lovely, now some of these things are faint, but I thought I'd put there usually. Interesting thing for photography. I've never seen, look at that gas cloud. Now that's one I've not come across before. So I've got some things in there that are unusual. So note these down, guys. Got this one, Roscoe? 6604. And right there, Ross records all these things so we know what we can image later on. 66, sorry? Yeah. Yeah, open clustering serpents, but it's the gas cloud around it that I think is really interesting. 1.5 degrees north of the Eagle. So there's one. Over here is probably something familiar to some of you, the Saturn Nebula. The problem with this is it is so small. It is tiny. And even when you enlarge it, look, fluorescent green tint comes from doubly ionized oxygen, so on in UV light, but look at the size of it. And this magnification. This is 470 with a Celestron 9.25 and a Pentax, my Pentax 5mm. So you're looking at a very, very small thing, very small. But the C14 might be a better bet because that's got 4 metre focal length. Small, yeah. So I put that up there because you often hear people talking. There's an old picture I took of the Eagle. So the Eagle's up there, right next to this new interesting area. So that might be worth investigating. Looking north, look at Capricorn. A couple of things about Capricorn. There are some interesting double stars here. Over here, beautiful globular cluster, but very, very small, disappointingly so. The jellyfish cluster, I think I've mentioned that in the previous talks. 90 light years across, but 12 arc minutes, it's not that big. But it has got a bright central core. But the interesting thing is it's the density. I couldn't believe this when I read about it. It's got 1 million solar masses per cubic parsec. That is incredibly dense. So the core is, say, possibly denser than Omega Centauri or 47 Tucana or any of those. So, wow. And because they're so close, they make binary stars and make blue stragglers, collisions. And next to it is a very bright star, 41. See that bright star there, 41 Capricorni, which is an orange supergiant from memory, I think. Now down here, Alpha Capricorni is a double star, a double system. So you've got the primary star, Algeta, yellow supergiant, and Alpha 2, 687 light years away, 6 arc minutes from the other one, an optical double. So they're not a real binary system, it's just a visual double. But still interesting to look at. That's a G8 evolved star. So you've got some nice colours here. Have you looked at these, Steve? Yeah. Underwhelming? No? Good? Yeah. Yeah. All right, so Getty, Prior and Prima and Secunda. Now Beta, up above, Beta, my little pointer's working now. Oh, it's become a, sorry. No, I don't want a magnifying glass. Yeah. Okay, a dubby, a multiple quintuplet star. Now have a look at this, the hierarchy. It's got a KO2 that's a bright giant, and a B8V, so it's a normal dwarf star, but a blue one, and an A system. So have a look at the hierarchy here. So you've got a triple system and a binary. And they orbit every 700,000 years. The triple and the double, I mean, around a mutual. 700,000 years. Hierarchy of orbits, yeah. Interesting. So that's a quintuplet star. Anyway, Saturn, well, a month ago it looked like that. On the 15th of September. Well, not a month ago, but a couple of weeks ago. You all remember these moons. We all remember the order of the moons, do we? I know. There's a lot to remember with Saturn. Anyway, the Sculptor galaxy. Lisa, you've taken a picture of the Sculptor. I've taken a picture of Sculptor, not as nice as the one Lisa's got with her Schmidt-Cassegrain, but it's a beautiful thing to take pictures of. It's quite big. This is with my new telescope. I'm pretending, I'm imagining now, because I haven't used it for anything yet, except for one night of viewing. At 117 magnifications, that's what you'd see. Now, it doesn't matter, any telescope at 117 magnifications, that's what you'd see, that's the field. So you need, but then at that magnification, depending on the aperture of the telescope, it might be really, really faint, smudgy, and not very bright. Of course, the C14 might be interesting to look at these galaxies still. Still faint, yeah. Anyway, the silver dollar, Sculptor galaxy is a very pretty thing. A couple of more pictures of it with a Teleview Panoptic 24 giving you, 34 magnifications. So the less of the magnification, the less you see, but the brighter the object. So it's always a trade-off, isn't it? Yeah. So a couple of other things. Now, NGC 300. Now, this is an interesting thing. Every time I look at this, I think for some reason, I think of triangulum, which is slightly a different kind of pitch, slightly different angle. Yeah, 21 minutes by 15 minutes is quite a decent size. Yeah. 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 Doesn't do any justice to it. No. I'll have to look at it. Yeah. Yeah. Some of the things I've got are challenging, that's for sure. Okay, so has it frozen? Yeah, I think we've frozen a bit there. Oh, stupid Kaspersky. Sorry, people. Won't be a moment. What is the matter with these people? I hate Kaspersky. It is annoying. Is it working? Sorry, just a minute. Oh, here we go. Where is my cursor? So I'll just go, just a minute. Sorry about this. I've lost control of this. Why can't I see it on here? Oh, I know. Hang on. Won't be a sec. There's P. Oh, no wonder. I've got it on duplicate. Now it's working. It was on extend. I didn't realise. Yeah, so now that's an interesting galaxy, the Whale Galaxy. Now that's something I'm going to take a picture of. Did you take a picture of this? Are you? So anyway, it looks quite bright and it looks an interesting object to take a picture of. Burnham calls it one of the outstanding galaxies of the southern heavens. Have you looked at that, Steve, through? Pretty? Mm. Mm.
I think the silver coin is a more classic view.
Yeah.
But still,
Oh, good. Well, there's one. Yeah, yeah. Oh, there you go. Now, here's a couple of things. So there are some views through eyepieces. The one at the top is using an APS-C sensor and a Celestron 9¼ inch. You'd fill the field of view. So, whereas down here, with a 24 panoptic observation, not photography, magnification of 30 near enough, that's what you'd see. Still be an interesting object to look at. Yeah, anyway. So there you go, the Whale Galaxy. Beautiful. So here we're looking northeast. There's a meteor shower too at the moment. I think it's still going. The southern Taurids. Looking south, the Spanish Dancer Spiral Galaxy. Now this is really small. I looked it up. I got very excited. Then I realised 8 arc minutes by 5 is not real big. So I got excited. Then it was a bit of an anticlimax. And you look at the size of it here. This is through an APS-C sensor and a Celestron 9¼ inch to give you an idea. It's pretty small. Sorry? Not bad. Oh. You've got enough detail there to get some, with long exposure you might, yeah. Now that's a Pentax 7 view, 117 magnifications. Yeah, it's about the same size, but from an observation point of view. And then finally, a couple of other interesting things down here. If we look at this area near the Southern Cross, now at the moment on Sunday night, I'm looking at this and I wanted to, what was I going to take a picture of in this area? Not the Statue of Liberty, the running chicken. I wanted to do the running chicken. And the running chicken was chickening low. And this was swinging around. But by the time I got ready to go home, which was 2 o'clock in the morning, this had swung around here and it was looking, and the false cross was over here and was looking more promising, you know. And I thought, if I went home, I should have stayed out. The geese were calling, you know, I loved it. It was nice. Still no more wind. The Mount Pleasant Blues were behind me. Anyway, let's look at that just quickly to finish up. Look at that area close up. There's some interesting things in here you might be aware of. Remember the good old Southern Pleiades, always worth looking through a telescope. Even though photographically they're not spectacular, they're still nice to look at. Very bright, scattered and loose but bright. And then you've got, that's a binocular view of it, 7 by 50 binocular view. Next to that, the Statue of Liberty. That's my picture of the Statue of Liberty. And then next to that, to the left, because remember we're upside down, is the beautiful Pearl Cluster, 3766. A lovely cluster to look at as well, and a rival to the jewel box. And then there's this. Now, have anyone imaged that before? 3572, open cluster nebulosity. It's not so much the cluster as this is really interesting. I've seen other pictures of it. And that's just near, here's the Statue of Liberty. So it's just over here. That might be worth noting. Get that one down, Roscoe? 3572. Why? Because there's another picture of it. Oh, sorry, on the right there. It's quite a beautiful, interesting cloud. So that might be worth investigating. And there's the old jewel box, not jewel box, the football cluster, gem cluster. It's a picture I took at the Wishing Well. It's the other name for it. And then down here, the hand cluster, which never appears, and I've only ever seen named the hand cluster by Stellarium. No one else gives it a name. But it has got an interesting shape. So there's one, Ross, you know, when you're imaging star clusters, that would be a nice one without a filter. Yeah. 3114. Right. And I think indulge me. I still like my favourite picture when I took this. Now, when I did this at Font Hill, I got up off the chair and there was ice on it. And it was 2 degrees. And the only person who lasted as long as me was Michael Booth, who's not here tonight. And I found out he was on the other side of the main kitchen area. And we were the only two. And I staggered to bed about 5 o'clock. And the only reason those stars are reasonably sharp is because of Blur Exterminator. Because the tracking wasn't good and my deck axis was sloppy in the Skywatcher. So it compensated for that. But I was frozen. But it was worth it. I'm pleased with that, even though it's not the best image, it's still okay. Anyway, so, and that thing there, in case you're interested, is 20,000 light years away and has nothing to do with this, which is 9,000 light years away. It's like they're superimposed or connected. So the one on the left, yeah, a superstar cluster at the middle, just like the middle of the tarantula, R136. Massive, supermassive stars at the middle of that. I think that's the biggest emission nebula in the galaxy. Something like that, I remember reading. And there are the clusters, there are the stars in the middle of it. Wow. Amazing. And finally, I think this is the last one. Yeah. The tarantula, as a comparison to what we just looked at, the tarantula, as many of us have noted before, and you did too, Dallas, I noticed on your website, if you put that where the Orion Nebula is, it'll cast shadows at night. So, now the biggest star in the R136A1 is 300 times the mass of the Sun. It's amazing. And I think it's like 7 million times the luminosity or something staggering. Anyway, 5 million times the luminosity. There it is, R136A1. So that's the same sort of thing. Now we were talking about the colour on Sunday night of the tarantula, and that's a classic colour scheme. So there is a sort of, not a brilliant red, a sort of pastel red and green, and with a bit of other stuff thrown in as well. Anyway, and there's another shot of R136. Oh, and that was I'll go back just one. That was a 7x50 on the top right there. There's a 7x50 view of the Large Magellanic Cloud, 7x50 binoculars. So you can still see some interesting stuff without having a telescope. Well, I've got another picture coming up. Yeah, so that one there, this one here, this is the 7x50. Now I'm going to show you a...
very, very fun.
Yeah. Yeah.
You didn't see that over. Right? You get to a dark side and spend time with binoculars late at night.
Yeah.
You'll see that nebulosity.
That was an early picture. I told you, Eugene, I'd take a picture. I had taken a picture of the tarantula long ago. That's a really old picture, that one. But notice, Roscoe, more stars than that, because I wasn't using a colour filter. There's more stars than that, like your picture on Sunday. So filters aren't always a great thing sometimes. Anyway, there are different views of the tarantula. This is through a celestron and the framing of a celestron and an APS-C sensor. You could see you just get the whole of the tarantula and that's it. No room for anything else. The true lover's knot is its other name, by the way. Using a panoptic, 50 magnifications, that's the view you get at 50, and then that's the view through 15x70. So looking at binoculars, Skymaster, Celestron Skymaster, that's what you'd see. But you need those things are a brick. You need a tripod. Yeah. And the last view is west. M83 is now setting. In fact, it's gone, I think, by this time now. So you can see Libra's setting here. Well, Libra's virtually gone. It's still a beautiful, beautiful thing, the southern pinwheel. I'll have to wait till next year to take pictures. Now, just one thing. Don't forget the middle of the head of the scorpion. We've got a fancy little graphic here. Do you like that? How do you like them apples? So it's a nice area to photograph. You've got the blue horse head down here on the right, the star Jabba, which is a septuplet star, and this beautiful row of Phaiki, which I've missed out on this year again, but perfect for a 135mm lens on a digital SLR camera or mirrorless camera. Up the top there, a picture of the whirlpool at 81 magnifications and then at 120 through an eyepiece. And finally, a framing using an APS-C sensor and, again, the Celestron 9¼ inch. I don't know why I keep doing that. I haven't got a Celestron 9¼ inch, but it strikes me as being a good telescope for our galaxies, and like the 8-inch. A nice focal length, 2,400 roughly, something like that. Yeah. Anyway, I think that's it. Beautiful things to look at in the sky. Meanwhile, back on Earth, here we go. Final page of the medical board's examination. What's the name of that thing that hangs down the back of our throats? I just love that. Anyway, does anyone know what the answer is to that? It's uvula. You know that little thing that hangs down? It's called a uvula. But every time I look at it, it just cracks me up. You know, you've done a great job in the exam. You get to the last question. What the hell is that? Oh, I love it. Anyway, thanks, folks. That was it. I told you it was short. That's it. But, I mean, you can only pick so many objects, but there's so much stuff up there to look at. But I always like to put in something that's exotic and probably you can't see, like the Saturn Nebula, but